Everyone, in our last lesson, we learned about internal resistance of a battery, and basically that no battery is perfect. So we have looked at a practical shortly, and for this lesson, I would like us just to go through the basics again, because this is, of course, a matric portfolio prac that you will be expected to do to determine the internal resistance of a battery. So this is the setup. And I would like you just to take note of the following. You've got your battery, you've got your voltmeter that is connected across that battery, you've got a variable resistor here, which we call, of course, a rheostat. And that is connected in series with another resistor of about 11 ohm, just to bring the total current in that circuit down so that you decrease the heat buildup in that battery. And you have an ammeter connected in series with these resistors to measure the current flowing through the external circuit, which will, of course, also flow through the battery. So just take note, please, that this is just a close-up of it. Your rheostat is basically a length of wire, coil of wire, and a slider that can slide, making contact with this length of wire. If you slide it all the way to the right, you increase the resistance to the maximum because you increase the length of this wire. If you slide it all the way to the left, you decrease the length of the wire to basically zero, and so the total resistance will be zero. The function, as I said, of this resistor here is to just bring the total resistance of that circuit down to decrease the heat buildup. You also need to make sure that when you do this prac, you connect your rheostat into that circuit for a short period of time, get your voltmeter reading, get your ammeter reading, and then disconnect again in the end to bring the total heat buildup down in that experiment. Just some pointers again before we look at this video, that the EMF is the voltage across the battery when the circuit is open. So when the current is actually zero, that means that the voltage measured across the battery will be your EMF. If there is no load connected to the battery, but the minute there's a load connected to that battery, the voltage across that battery that we measure, when charge is flowing through that battery, that voltage is called the terminal potential difference. I would like you just to have a listen to this.
Now, calculating the internal resistance of a cell is a kind of key practical that you need to know about. It's often brought up in exam questions. So what we have is a fairly new cell here, which we can then measure. We've got a voltmeter, we've got an ammeter, we've got a switch, and this thing here is a variable resistor. Now, sometimes you get a little kind of box that you just twiddle a dial on. Sometimes you also get a thing which is basically a big coil of wire with a slider on top of it, and that's called a rheostat. But basically all this does is it changes the total resistance of this external part of the circuit to the cell. Now, when it comes to doing the experiment, what you do is you basically just set it up, you close the switch, you record the potential difference and the current, you then adjust resistance and do that many more times. When you get 6 results, you can then plot a graph. So the results that you're going to take should look a bit like this. So you're measuring the potential difference across that thing there, which is called the terminal PD, because it's the potential difference of the battery terminals. And we also have our current measured in amps. What you can then do is actually think about the equation. Now, the equation for internal resistance and how that links to EMF is that EMF is equal to the potential difference plus IR, where I is the current in that circuit and little r is our internal resistance. If I rearrange this equation, I can also say then that V is equal to E minus IR, and I can then also say that V is equal to minus RI plus E. So it's just the same equation, just rearranged in this form. The reason this is important is if we can think about the equation for a straight line, we can say that y is equal to mx plus c. Now what that means is if you plot the potential difference on the y-axis and you plot the current on the x-axis, the gradient and the y-intercept then actually mean something. And what you'll find is that when you have a greater and greater current flowing in that circuit, the internal resistance is going to have a bigger effect and effectively cause what we call more lost volts. And that means we get a graph that looks a bit like this. Now, what does the gradient mean? Well, a gradient is going to be equal to minus the internal resistance. So the gradient is going to be equal to that and the negative value of the internal resistance, and the y-intercept here is effectively the true EMF of that battery. So if it's a 3-volt EMF, effectively we only get the maximum energy out of it when you have no current flowing, and therefore the internal resistance has no effect on it. So that's pretty much all there is to it, okay? So yeah, that's it pretty much. Set up the circuit, 6 good readings with a nice range. Remember to take repeats and then find your mean values. Plot V against I on the graph, and then your gradient is going to be equal to the negative value of the internal resistance of the cell.
So with that in mind, we are now going to look at a problem. So I would just like to remind you of that internal resistance formula that you have to use going forward, and that is that EMF is a product of current and the external plus internal resistance of that circuit. That, of course, also means that EMF is equal to V external plus V internal, or the voltage across the internal resistance, which we simply call V lost. So please take note of these two equations. They are very important. So you're given this setup with all the equipment that I've mentioned to you. And it says that Thulo and Tatenda are required to investigate the relationship between potential difference V applied across a variable resistor and the current in the variable resistor. They are provided with the apparatus and circuit diagram shown below. So of course your battery has internal resistance. As you can see, it's not just a normal battery. It's got, number one, your internal resistance drawn in and your broken line block surrounding that. You can even do a circle around or some sort of oval, but as long as you show that block around the battery to show there's internal resistance. You've got an open switch, you've got your variable resistor, your voltmeter across, and you've got your ammeter reading the current. So 6 readings at least have to be taken by sliding the contact of the variable resistor at a certain position, and it reads then out the values. Thulo reads out the values of the potential difference across the rheostat and the current in it. So they get, in fact, 8 readings of that, sliding your slider, making contact with this rheostat wire from some resistance to some other extreme resistance. And now, as the voltmeter reading decreases, your current will increase. So clearly they have slid that slider from a very high resistance to a very low resistance. You're given these points. This is the terminal PD, and this is the current going through the external circuit, but also going through the battery. And you now have to draw a graph of these results. But first, we ask you to calculate the internal resistance of the battery of the cells by making use of the readings 3 and 8. So if you look at reading 3 and 8, here they are. You've got the potential difference, the terminal potential difference and the current, and then another set of terminal potential difference and current values. you need to work out the internal resistance of the battery, right? Now, the internal resistance of the battery you'll be able to calculate that by working with the voltmeter reading across the external circuit, because that will be exactly the same as the voltmeter reading across the battery, because there is only one resistor. But the minute there were two resistors, you have to actually put this voltmeter reading across the battery to work out the internal resistance of the battery, as we've explained in that experiment. So you take your values for reading 3. You're going to use your EMF formula, which is V load plus V lost. The EMF you do not have. The V load you can get from reading 3's terminal potential difference is 3, and the current will be 0.9. You substitute that into V lost. V lost is expanded as I times little r, and that gives you EMF is equal to 3 times 0.9 little r. Call that equation 1. For reading 8, you have 0.5 as your voltage and 2.2 amp as your current. EMF is therefore the V load, which is that external voltage right here, plus the current of 2.2 times little r. So we now say that we can call that equation 2. You have 2 unknowns, so you need 2 equations to solve this, and so you need to do simultaneous solving of equations. So if you set equal equation 1 to equation 2, because these right-hand sides are equal to the same metric or variable, EMF, then eventually what you work out is that the internal resistance is equal to 1.90. On to the next question. You are asked to then plot this graph of potential difference on the y-axis versus current on the x-axis. If you plot the points very carefully, and I want you to do this in this question, you will find that you have an indirect proportionality between potential difference and current. As we have discussed, your EMF will be your y-intercept, and where you basically short circuit the circuit, your potential difference will be 0 and your current will be a maximum, because there's a surge of energy through that circuit, and that will give you your x-intercept. So you could also work out, of course, the gradient of this graph, and the gradient of the graph, as you know, is equal to minus r. Just again, how do we rearrange that to get to that form? We know EMF is V load plus V lost, which is I times little r. If you want V load or V external, this of course is V load. On the y-axis, you need to rearrange it so that you do get V external or V load on the y-axis. That will give you EMF. Take away I times little r. Current is, of course, on the x-axis, and so what you should do is the following. You need to get this in the form y equals mx plus c. So the external is going to be, let's just undo that. All right. The external is going to be negative small r multiplied with a current plus EMF. This now mimics the straight line graph equation y equals mx plus c. Immediately you can see that c is your EMF, or the y-intercept is equal to your EMF. And you can see that the gradient is equal to negative r. And the gradient, of course, you're going to work out by rise divided by run. You are now asked to indicate the value for the EMF on the graph, all right, and the current when the battery is short-circuited. As I've said, the EMF is the y-intercept, and the current when the battery is short-circuited, that is where you have a maximum amount of current, but 0 voltage will be the x-intercept of that graph. You then have to use the graph to determine the internal resistance of the battery and compare the values, this value that you get here with the value of the internal resistance you worked out theoretically in question 4.1. So, of course, you need to draw a line of best fit through these points. And in order for you to now work out the gradient, you're going to have to choose 2 points on this graph that exactly lies on the graph. And that'll be the second and the last points. So you need to get the coordinates of those points. And then, of course, get the rise divided by the run. And you need 2 values for y and 2 values for x to subtract and then get that gradient. That gives us the second point being, let us see, so the y values will be 0.5, take away 3.5. If you go look at it, all right, this point's y value is 0.5 and that point's y value is 3.5. So we can say 0.5, take away 3.5, divided by this x value of about 2.2, take away this x value of 0.5. Is that correct? Yes. So it's 0.5 minus 3.5 divided by 2.2 minus 0.5 equals, and you're going to work that out, negative 1.77 ohms about. That is the gradient. What do we know the gradient is equal to? Well, that gradient is equal to negative R, and that means that the internal resistance is a positive value, as it should be, of 1.77 ohm. The question is now, which of these 2 values, the theoretically calculated value for internal resistance 1.92 ohm, or this value calculated by the gradient of the line of best fit of the data, is more correct? Which one is more correct? Before I answer that, I want you just to have a look at this. There's a question asked to you. How can a graph of data be more informative than a table of the same data? Now, scientists, of course, gather data. The more data they can gather, the more accurately they can plot those data points on a graph to get a line of best fit, to give you some sort of trend in the data for them to then interpret that graph and the relationship between the metrics that you are measuring. So, first of all, a graph provides a visual informational view instead of just simply being numbers on a table. You need to know that some of the numbers may be anomalies, meaning they are outliers, and using them in a theoretical formula to work out whatever metric you want to work out will increase the percent error from the accepted value. The more data collected, we said, the more points can be plotted on that graph for a more accurate line of best fit that graph. And of course, the graph represents a more accurate value of the metric that you want to calculate. So tell me, with this now in mind, which of these 2 values, the theoretical value of 1.92 ohm or the gradient of this graph of the data being the internal resistance of 1.77, which one is closer to your accepted value or the accurate value? Which one is more accurate? Of course, it will be this one that you work out from the graph, because that tells you the trend that lies within that data. It excludes anomalies, any sort of outliers not lying on that line, and of course you had to take values that lie on this graph, and that gives you a much more accurate picture of the trend within the data than just choosing any 2 points. Of course, the 1 point used up in the previous question was 0.3 and 0.8. 0.3, as you can see, is an anomaly or an outlier, and we've used that. And of course, that will increase your percent error from the accepted value, your accepted value being your most accurate value of the trend of the data being 1.770. Of course, we can now look at a concept called amp hours. Now, we know that batteries aren't perfect. That is not the only thing you must know about batteries, that they have internal resistance, but you also need to understand what battery capacity is. So I want you to have a listen to this, please.
What's up, YouTube? This is LDS Reliance. We use batteries in our everyday life all the time, but not very many of us know really how they work or understand much about their characteristics. One of the biggest questions that I get asked is about capacity. Capacity means the actual quantity of electricity that you can extract out of a battery from one cycle of fully charged battery to fully discharged battery. So how do we measure capacity? Well, you may have noticed on some batteries, like this Power Tool battery, a measurement that says 4.0 AH, or 4.0 amp hours. And an amp hour is the amount of energy charge in a battery that will give you 1 amp or 1 ampere for 1 hour. So that's pretty simple, but unfortunately it gets more complicated. Most battery manufacturers do not all use the same measurement for calculating amp hours or capacity. Some of them will use a 10-hour rate, meaning it takes 10 hours to discharge the battery. Other people will use 20, and others will use 100. So you need to make sure that you look at the fine print on the label. So here's an example of a battery that uses the 100-hour rate. If you were to compare this to a 20-hour battery, you would think that this was much better. However, you need to convert the run rates to the same measurement to be able to compare them accurately. So what does this all mean? Well, let's take a 225 amp hour battery, which is measured at the 20-hour run rate, and do a simple math problem. So you cross out the hours on the top and the bottom, and you divide the top by the bottom, and you get 11.25 amps. And what that means is that this battery is rated to produce 11.25 amps for 20 hours straight. So the last thing that I wanted to mention in this video that's very important is that the more current you draw, the more you lower the capacity of the battery. So in this chart, as you'll see on the right side, the furthermost extreme is 0.33 amps. This battery will run that for 20 hours. But if you were to draw 32.5 amps, it'll only last 4 minutes. So keep that in mind when you're talking about how much battery capacity you need for a specific application. Thanks for watching, guys. We'll see you next time.
Hello and welcome to my lab. Today I'd like to talk to you a little bit about batteries that you'll be needing for your solar panel to store some of that hard-earned energy. When you go shopping for a battery, you'll notice that the batteries are rated in amp hours. And amp hours on their own are really quite meaningless unless you know the voltage behind it. They're closely linked to determine the wattage. And the essential is a simple multiplication. You multiply the amps times the voltage, and that'll give you the watts. And here it is. Amps times voltage will give you watts. And so if you have a battery that's rated at 10 amp hours times 12 volts, that will give you 120 watt hours. Essentially what that means is you could use 120 watts for 1 hour, or 1 watt for 120 hours. Let's compare 10 amps here with the household current that you have. Let's pretend let's use a dryer or a microwave, say, that uses 10 amps. That would be 10 amps at 120 volts, which would amount to 1200 watts. So there's a factor of 10 difference there, and it's significant. So don't let yourself be fooled by big numbers on a battery, because you cannot compare that with your home. It's completely different, and something that you'll want to pay attention to as you're shopping for a battery. Thanks kindly for listening to me, and we'll be talking to you soon. Thanks.
Right, so what have you learned here? Basically, that you cannot look at the amp hour rating on a battery and look at the high value, say it's 225 amp hours, and say, oh, look at that high value. I'm going to get 225 amps at all times, whenever and however long I use this battery to do work for me, right? Because as this guy said, you have to multiply it with the voltage across that battery. And of course, you multiply the two together to get watt hours. Watt hours is, of course, something much more useful because it will tell you how powerful that battery will be for a certain amount of time, how quickly it will discharge, how long it will take, and how much power it needs for a certain amount of time to recharge as well. And that is very important when we start looking at things like solar panels. You want all of that energy that you have stored from the sunlight and then stored into your battery to actually be converted into power, to power appliances in your home for a long period of time. You don't want it to discharge very quickly. So it's very important, this concept of amp hours multiplied with voltage to get watt hours. That's the capacity of the battery. This is absolutely brilliant. It gives you a summary. This video, please go click on it and watch it. Gives you a summary of voltage, current, AC versus DC, power, the watt hour, calculating watt hour rating of a battery, and parallel and series or parallel series combination connections. This is absolutely brilliant. It gives you a good perspective of everything we have done in this chapter, and it will just confirm it for you again. Your homework will now be to do pages 76 to 78. Skip page 79, you're going to do page 80. Skip page 81, and you're going to do page 82 to page 84. And this, of course, is another of my friend's paintings, and it marks the exit now that we are making from electrical circuits. I hope that you have enjoyed this section and that you will be doing well in it. Please make sure that if you do not understand anything, or if you don't understand something, any section of this topic, that you please revisit that section in the notes, that you re-watch my posted teaching videos on Classroom and YouTube, and that you do past papers after you have gone through all of this. Please make sure that you go through the syllabus and through the SAGs to find each point, bullet point, that you need to know for this section, please. All right, that concludes the section. This is our exit, and I've enjoyed doing this section with you. I hope that you have enjoyed doing it with me, this section on learning about electricity. I will see you in our next lesson. Thanks for joining. Bye-bye.